Now we'll discuss section 2.4, formula mass, molecular mass, and molar mass. So we've learned about formulas and how to write the chemical formulas. How does this relate to the mass of the material? So this helps us determine how many particles are present. Using the formula units and the mass of a sample and the periodic table, we can determine how many atoms, molecules, or ions are present. So we'll start with the atomic masses listed on the periodic table in units of AMU. Remember that 1 AMU equals 1.66 times 10 to the negative 24th grams. So this is a very, very, very small amount of material, or of mass. So how do we figure out the formula mass of water, H2O? Each H has a mass of 1.007 AMUs. Each O has a mass of 16.00 AMUs. And we get these numbers from the periodic table. So we look at hydrogen. This table says 1.008, close enough to 1.007. For oxygen, we look at the atomic mass, 16.00. So we'll use these numbers on the bottom now. So we add them up. 2 times 1.007, 2.014. Oxygen, 16.00. Add them together, 18.041. The molecular mass for water is 18.01 AMUs to 2 decimal places. Because we're adding, we have 2 decimal places here, 3 here. We want to keep 2 decimal places in our answer, 18.01 AMU. And that's the mass of 1 water molecule. If this were an ionic compound, the sum of the masses is the formula mass for the compound. So let's calculate the molecular mass of methane and also calculate the formula mass of aluminum hydroxide. So for methane, C equals 12.01 AMU, and we'll see that right here. C, 12.01. We'll use the formula mass for hydrogen, 1.008. Oh, that should be an H. Equals 1.008 AMU. We add that together, 12.01 plus 4 times 1.008. Using our calculator, that gives us 16.043 AMU. And now we added them, so we want to have only 2 decimal places in the appropriate, or in the answer. So 1604 AMU is the best way to record the answer. And this is the mass of 1 molecule of methane. 1 molecule, 16.04 AMU. So the formula mass for aluminum hydroxide, aluminum, 26.982 AMU. We can check that on the periodic table here. Aluminum, 26.98. So the periodic table I used has another digit on it, 26.98. And we have 3 oxygens, 3 times 16.00. 3 hydrogens, 3 times 1.008. We add them all up, 78, sorry, that should be an 8, 006 AMU. So we round that, 78.01 AMU, keeping only 2 decimal places, rounding this 0 to 1 because it's a 6. So that's the mass of 1 formula unit of aluminum hydroxide. So now work one on your own. What is the formula mass of nitrogen dioxide, NO2? So working this, we need to look up the mass of nitrogen, 14.01. Add to it 2 times 16.00. 16 plus 16 is 32. Plus 14.01, 46.01 AMU. So D is the best answer here. 16 plus 16 plus 14.01. So how does this help us? Really, an AMU is too small to be weighed. The balances that you got in your lab kit, they can weigh out on gram quantities and milligram quantities, but an AMU is 10 to the negative 24th grams, so it's a very, very small amount. So a scientist named Avogadro and some other scientists determined a conversion factor to get to real-world amounts that we can hold in our hand or measure on a balance, and that's called a mole. And this lets us convert between grams and numbers of objects, so that weighing a sample will ultimately tell us how many molecules or formula units are present. And so determining the AMU for a molecule or a formula unit is the first step in this conversion. So the mole is a unit of counting, just like a dozen, a pair, a gross, and a ream. It simply is a word that stands for a certain number of objects, just like a pair stands for 2, a dozen stands for 12, and so forth. The mole stands for 6.02 times 10 to the 23rd objects per mole. So that's a lot of objects. There are very, very many objects in a mole. And it's also sometimes called Avogadro's number, and it might be abbreviated instead of MOLE, MOL. Not that much of an abbreviation. The American Chemical Society has as its mascot an actual fuzzy mole, just as a sort of joke, tongue-in-cheek with the mole. And here's a mole of sugar, a mole of copper, and a mole of water. So each of these three samples here has the same number of atoms or molecules present. Notice they come in different quantities because the unit formula for each of these three are different, and so they have different masses. So the same number of objects will have a different amount of mass because each individual object weighs different. So just to get an idea of how much the mole is, if we had a mole of textbooks, if we all had the hard copy text for our Essentials of General Organic and Biochemistry, it would cover the entire USA to a depth of 200 miles. So we'd cover the entire surface of the US, and we'd build that layer up to 200 miles thick. It takes 134,000 years for 1 mole of water droplets to flow over Niagara Falls. 134,000 years for 1 mole of water droplets. And if you've ever been to Niagara Falls, you know how much water is flowing over those falls every second. And to imagine that it takes 134,000 years to get a mole of water droplets, that's an incredibly large amount of water droplets. If we took a mole of marbles, we could form a mountain 116 times higher than Mount Everest. We had a mole of marbles. So what does Avogadro's number do? What can we do with this number mole? 6.02 times 10 to the 23rd objects in a mole. It allows us to measure substances in grams and know exactly how many particles are in the sample. Essentially, we're going to come up with a conversion factor that will allow us to convert from grams into the number of particles. So, for example, one conversion factor is the molecular mass of carbon dioxide. 44.011 grams per mole. So that tells us there are 44 grams of carbon dioxide in 1 mole of carbon dioxide molecules. That's a conversion factor. We can convert between mole of carbon dioxide and grams of carbon dioxide. If we use, we calculated water as having a mass of 18.014 AMUs per molecule. That's the molecular mass, the mass of 1 water molecule. We can simply take that number, change the units, AMU per molecule, into grams per mole to get to the molar mass, the mass of 1 mole of water molecule. So that's where calculating the AMU, the mass in AMUs, is useful, because we can just replace that unit, AMU per molecule, with grams per mole, and we have the molar mass of water. So we know that water is 18 grams in a mole of water. CO2, 44.01 AMUs per molecule, or 44.01 grams per mole. So calculating the molecular or formula masses gives us a conversion unit of grams per mole. And we use AMU if we're talking about individual molecules. Typically, chemists talk about moles of molecules, so we use grams per mole as the unit. We use grams if we have a mole of molecules. Clicker question 2.9. When calculating molar masses involving carbon, we should use what? Well, we should look on the periodic table and see what the number is. Typically it's given as 12.01. That's the average mass of carbon atoms, of a carbon atom. And so we should use 12.01. Since it's the molar mass, we should use 12.01 grams per mole, D. So why do we need to go through this? Well, if we wanted to buy the same number of apples as cherries, right? If we wanted to buy a dozen of each or 100 of each, would we order a pound of each? Right? So does a dozen apples weigh the same as a dozen cherries? I think we'll all agree that it doesn't, right? An apple certainly is larger than a cherry. It weighs more than a cherry. So a dozen apples will weigh a lot more than a dozen cherries, and so we cannot measure them out as the same amount. We have to measure them out, either count them out, or know how much each individual apple weighs. So the same is true of molecules. We don't weigh out 1 gram of water and 1 gram of CO2 and react them together because they're equal amounts. We need to weigh out them in terms of their molar amounts. So in a chemical process, molecules interact by their number and not by their weight. So when we weigh things out, we want to know how much is there, how many particles are there, not what mass is present. And we may use a small sample size. So we might be using fractions of a mole. We can use the same prefixes to describe the magnitude of moles as we use for mass. So millimole, small m, is 1,000th of a mole, 10 to the minus third, or 0.001 moles. A micromole, with the Greek letter mu, is 1/1,000,000th of a mole, 10 to the minus 6. And blood tests often report levels of molecules or ions using these smaller versions of the mole, millimole or micromole units. So let's think of some more practice problems here. Which has a greater mass, a mole of ping pong balls or a mole of basketballs? So if we have the same number of ping pong balls and basketballs, which one weighs more? Certainly I think we'll all agree a mole of basketballs. And why is that? Well, one basketball weighs more than one ping pong ball. And this is the same thing with molecules. Most molecules have different weights. So if we want to have the same number of molecules, we need to weigh them out in terms of a mole, not in terms of grams. So what is the average atomic mass of one mercury atom? Well, if we look at the periodic table, mercury is kind of funny. It's Hg. Hg is located down here. It's element number 80. And if we look carefully at this periodic table, it says that the atomic mass of mercury is 200.6. So the atomic mass of one mercury atom, 200.6. And now we need to be sure to use the appropriate units here. Remember that AMU is used to describe the mass of one molecule or one atom. Or one particle is the better way to put it. So 200.6 AMU for one mercury atom. How about a mole of mercury atoms? Well, we use the same number. We just change the units. 200.6 grams in 1 mole of mercury atoms. So now we have a mole, we use grams. We had one particle, we use AMUs. How are they similar and different? Well, they have the same number, of course. They just have different units. So when we're talking about particles, we use AMU. When we're talking about moles of particles, we use grams.